Welcome back to chapter 25. This is our fourth video. We'll look at two examples that utilize Snell's law. And we'll also practice some of these in class. So we're going to start out with our example. We're going to have a fish tank, and light's going to come in from one side of the fish tank, pass through the first glass wall, pass through the water, pass through the second glass wall, and then exit out into the air. And what we want to figure out is if we know the light comes into the tank at a 20-degree angle from the air into the glass, what angle is it going to exit out on the other side? It's a matter of taking these changes step by step. So it's important with these pictures to have a good diagram. You want to make sure you understand your layering. You'll notice that we have all these dashed lines. Those are normals to the surface. So when the light ray comes in and hits the glass, this 20-degree angle is between the normal to the surface and the light ray. Remember that a normal to the surface makes a 90-degree angle with the surface. So we'll be measuring our angles with respect to these little dashed lines that hit our surfaces at a 90-degree angle. We need to know the index of refraction for the different materials. So we'll need it for air and glass and water. Those are our three materials. And we'll need to know the incident angle and Snell's law. Remember that Snell's law was n1 sine theta 1 equals n2 sine theta 2. So now we have our diagram, and we need to come down and look at our summary of information. So the index of refraction for air is 1.003. For water, it's 1.333. And for this particular glass, it's going to be 1.5. I'll have to give you these indices of refraction. You would never be expected to memorize them. You'll always be able to look them up in a table. And we're going to find all our angles as we go along. So we just take it one interface at a time. An interface is the boundary between one medium and another. So we start out in air and enter glass. So we're going to look at the air-glass interface. We'll look at the air-glass interface. So as we come down, every time I do one, usually what I do is summarize the information. So I know what is my medium, air, what's its index of refraction, and what angle are we dealing with. So we're in air, the index of refraction is 1.0003, and the angle we have is 20 degrees. We're going into glass, its index of refraction is 1.5, and we don't know the angle. So our 20-degree angle would be this little angle right here. And the mystery angle is this angle right here between the exiting arrow and the dashed line. So we just start out with Snell's law. N1 sine theta 1 equals N2 sine theta 2. And I know in the drawing it's whoops, hard to tell, but this 1 was supposed to be a subscript. So it's N sub 1, not N multiplied by 1. So N1 sine theta 1 equals N2 sine theta 2. 1.0003 times the sine of 20 degrees equals 1.5 times the sine of our exiting angle. When you do the math, the sine of the exiting angle ends up equaling 0.22808. Now, to go from this number to the actual angle, you would on your calculator punch second function or inverse, depending on your calculator. There's a key for that. So it's either the second key or the inverse key. And then you'd hit the sine key and 0.22808 and then equals or enter. And you should end up with 13.18 degrees. You should end up with 13.18 degrees. If you don't know how to go from sine theta equals 0.22808 to theta equals 13.18 degrees, you need to ask me for help, and I will show you how to do it on your calculator. So now what we know is this little angle. So that's the angle where we enter the glass at, 13.18 degrees. All right. So now we're going from glass into water. So again, we're in the glass. We know it's 13.18 degrees. And we want to know what angle do we enter the water at. So again, N1 sine theta 1 is N2 sine theta 2, but now we're starting in glass. We have our angle, we have the index of refraction for the water, and we're solving for the angle in the water. So when we plug in, we end up with 14.9 degrees. And as you go through the arithmetic, if you need help with anything, you need to let me know. So now we're in water. We need to go from the water to the other side of the glass. So we're working our way through water to the other side of the glass. So we know we start out in the water at 14.9 degrees. The index of refraction for the water is 1.33. Glass, it's 1.5, and we need to know the angle. So again, it's just Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. We plug in our numbers, we do the math, we end up with 13.17 degrees. That would be this angle, the angle that we're in the glass, and it's the angle we exit the glass on one side. And then finally, we're going to go glass into air. So we know the glass information, both the index of refraction and its angle. We're exiting into the air. We know its index of refraction, and we're solving for the angle. So N1 sine theta 1 is N2 sine theta 2. Plug in the numbers. You get that sine theta 2 is 0.3417, and surprisingly enough, when we scroll down, you will see that the angle we exit at is also 20 degrees. You should remember that that's the same angle we started at. So we come back and look at our original picture just for a minute. We're going to go back and look at the original diagram just for a minute. What we have just discovered is that the angle we exit at is 20 degrees, and that's the same as the angle we entered at. The reason that's true is because of symmetry. We go air on the left, air on the right, glass on the left, glass on the right, water in the middle. If we folded this diagram right down the middle, the sides would match up. Because all of the interfaces are parallel to each other, and because of the symmetry of materials, the entrance angle and the exit angle are the same thing. So we could have said by symmetry, if we enter at 20 degrees, we're going to exit at 20 degrees. And again, it only works because we have air and air, glass and glass, water in the middle, and all the materials are separate from each other by these nice parallel lines. If any one of these lines had been at an angle, if this line had been at some sort of a diagonal angle, we would not have gotten the same answer. We would not be exiting at 20 degrees. If one pane had been glass, but the other had been plastic, we would not be exiting at 20 degrees. So it's all about the symmetry. All right, let's look at a non-symmetrical problem. So we'll come down and look at light entering a prism. So you have a right triangle, it's a prism, and we have our three angles, a 40, 50, and 90 degree angle. We're going to have light enter the prism at 45 degrees. And you'll notice I've got an alpha and a beta. Those little diagrams are going to come in handy. We'll need to know that before we're done. Because as you can see, we don't have any one of these lines parallel to the other. So symmetry is not going to help us. Symmetry will not be helpful. So the first thing we do, we're going from air into glass. We know this angle, it's 45 degrees. We need this little angle. Notice that this little angle is not alpha, it's not beta, it's this funny little space right here. So that's the angle we'll be solving for. So I've only drawn part of our diagram. Here's part of it. This is just the line. Here's the light ray coming in. Here's our 45-degree angle. And we know we're in air. We know we're going into glass. And we have the index of refraction for air and the index of refraction for glass. So it's just like the previous problem. N1 sine theta 1 is equal to N2 sine theta 2. We plug in our numbers, we do the arithmetic, and we come up with theta 2 is 28.1 degrees. 28.1 degrees. That is this angle, all right here. This is our angle, but we actually need this angle. So how are we going to do that? Well, if you'll notice from the picture, the two angles, the one we just found, the 28.1 degrees, and the one we need add up to 90 degrees. So I can take 90, subtract 28.1 from it, and have this little angle right here. And if you look back in our diagram, you will see that that little angle I'm going to solve for is alpha. We're going to find alpha from our original picture. So this is that 50-degree angle point on our original diagram. So that's the top point in our prism. Here's that 28.1 degree angle that we know. This is alpha that we need to find, and we're actually going to need beta too. So I've already said that 90 is going to equal alpha plus that 28.1 degrees. That means alpha is 61.9 degrees. We also know that the three angles of any triangle add up to 180 degrees. So 50 degrees plus alpha plus beta adds up to 180. Well, we know alpha, we just found it to be 61.9 degrees. So I can solve for beta and find out that it is 68.1 degrees. Now that I've got beta, I'm going to actually find, if we went back to our original picture, just a second, we know beta. We're going to use beta to find this angle right here. And we need that because that is theta 1 for our last calculation. If we want to find this exit angle, we need the entrance angle. And we get it because we know beta. Okay. So moving back down, we found that beta was 68.1 degrees. Now, we know that beta plus our new theta 1 that we want to find have to add up to 90. So theta 1 is 21.9 degrees. That's the angle that the light makes when it goes between glass and then exits into air. And so all we have to do is find the angle that it enters into the air at. And for that, again, we use Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. So we plug our numbers in. We're in glass on the left, air on the right. When you solve, you end up with 34 degrees. So we end up exiting that glass prism at 34 degrees. Again, this is something that requires a really careful attention to the original drawing. I'm sorry I couldn't kind of keep it in the frame as we went along. And this is where our video will stop. So we'll stop the share and stop the recording.